Alright, so now we're going to learn how to calculate the voltage or the cell potential for a particular reaction. So if we combine this metal with this solution, how much voltage is going to be produced? Before we do that, we need to talk about standard conditions. So all of our calculations are going to be based upon standard conditions again, which means that the concentration of reactants has to be 1 molar, same thing with the products. If it's a gas, pressure is at 1 atmosphere, and temperature is at 25 degrees Celsius. Conditions like that always have to be matched in order to be the standard conditions. And what that means is you're going to be calculating the E standard of the cell. So let's talk about standard reduction potentials. And the key word here is reduction. So all of the potentials, and that's going to be a list, are going to be showing reduction half reactions. And we can combine 2 half reactions together, make a whole reaction, and use that to then find the E of the cell. And so this is what it's going to look like. We'll have something like copper 2 plus 2 electrons. What we're showing here is a reduction because it's gaining electrons, forming copper solid. And over here on the side it says the E of this reduction, so the standard potential, the voltage generated by this reduction reaction, is 0.34 volts. So here's a small version of a standard reduction potential table. So what you see here is a bunch of reduction reactions, and then how much voltage is generated by this particular reduction reaction. And you can see that some of them are positive and some of them are negative, and other ones like this one right here are 0. And the more positive a number is, remember, E of the cell, that's the cell potential. And so if it's more positive, like silver, absorbing 1 electron at positive 0.80, that means it has more potential to occur. So this reaction is more likely to occur than, say, copper absorbing 2 electrons, which has a cell voltage of 0.34. And so with a higher positive number, therefore it has a higher potential to actually occur. Whereas something really, really low like this, that's a negative number, that means this reaction right here won't occur naturally. Okay, it's a negative value, and so that would be a non-thermodynamically favored reaction. And these charts are typically laid out like this, with the most positive number at the top and the most negative number at the bottom. And what it does for us then is as we go up, we increase the ability to attract electrons. So that's the ability to be reduced. So the top one on here is the most likely to be reduced. And as we go down, we increase the ability to lose electrons. So actually, aluminum, being at the bottom of the chart, is the most likely to lose electrons, and silver at the top of the chart is most likely to gain electrons. And so then as you go up the chart, that means you're increasing the likelihood of being the oxidation agent. So whichever one of the 2 half fractions is higher is going to have the oxidation agent, and then whoever's on the bottom would be the reduction agent. So then what does this mean to us? Well, let's imagine that we have ourselves a voltaic cell. So we have 2 different electrodes of 2 different metals, and then we have them both in their solutions, and then we've got a salt bridge in the middle, and then a wire connecting our 2 electrodes with a voltmeter in the middle, something to measure volts. So let's say that the electrode here on the left is copper, and the electrode here on the right is silver. Now if we wanted to figure out which one of those is the cathode and which one is the anode, so where does oxidation take place, where does reduction take place, that's where we go to our CERP table, this guy right here. So of copper and silver, which one is most likely to gain the electrons? Which one is most likely to take the electrons? Well, so if we find right here is copper and right here is silver, we see that silver is higher, so it is most likely to take the electrons, which means the half reaction occurring here is going to be Ag plus 1 electron turning into Ag. And so then copper is lower, and so it will not be reduced. Instead, it's going to have to be oxidized because it's lower on the chart, therefore it's more likely to lose electrons. So we're not going to write the half reaction just like that then. We have to flip it to show it losing those electrons. And so instead it's going to be copper solid turning into Cu2 plus 2 electrons. So what that means then is the electrons are going to flow from copper over to silver. And so our silver side reduction is taking place there, so that's going to be our cathode. And oxidation is taking place over here, so this would be our anode. So if we want to calculate what the standard cell potential is, so what the voltage is of that particular galvanic cell that we set up, here's the equation that we would use. So we would have the E of the cell, that's what we're trying to find, is equal to the potential of the cathode and the potential of the anode. So the cathode, that's where the reduction takes place. So this would be the one that is higher on the chart, and it's going to be most likely positive, which means that it has more potential to occur, and it's going to stay as written. The anode, however, this is where the oxidation takes place, and so we're going to have to take our reduction potential and flip it. So in our galvanic cell that we drew, we took copper and we flipped it as it appears in the SERP table, and so the E or the potential was 0.34, but since we flipped the reaction, moved the reactants over to the product side, it is now going to be a negative 0.34. And then silver's reduction potential was 0.80. So the cell potential, the amount of voltage that would be generated by that cell that we drew out, as long as it was at 25 degrees Celsius and both of the solutions were 1 molar, would be 0.80 plus negative 0.34. So that means the volts generated by that particular cell is going to be 0.46 volts. So here's another example. We have one nickel electrode and one copper electrode. And if we want to figure out what the cell potential is, we would have to look at our SERP table. And so in this case, both of them are given to us. Here's our copper, here's our nickel. And so we can see here that the copper is the more positive number, which means that one is going to stay as written. Nickel, on the other hand, is more negative, which means it's most likely going to be the one that's oxidized. And so we're going to have to take and flip that reaction. So we take that half reaction and we flip it just like this, and when we flip the reaction, we flip the sign, so it goes from a negative 0.25 to a positive 0.25. And then to figure out the E of the cell, we would just add those two guys together, and so 0.34 plus 0.25 is going to be 0.59 volts. Okay, and one more practice problem then. So in this case, we're looking at silver and nickel, and we can see that silver is still the most positive number, so it's going to stay the same. Nickel, on the other hand, negative. It's got to be oxidized, so we're going to have to flip that one. So we flip nickel, we flip the sign, it becomes a positive 0.25. Now, something to notice from this reaction, we see here that silver gains 1 electron, and nickel loses 2 electrons. Well, if it loses 2, where's that second electron going? Well, it means this reaction is not balanced. So in order to show the loss and gain of 2 electrons, we're going to need 2 silver cations picking up 2 electrons to produce 2 silver. However, this makes absolutely no difference to the cell potential. Even though we doubled this one, we do not double the potential. A change in balancing makes absolutely no difference to the cell potentials. The reason for that is the cell potential of silver is limited by the nickel. So even though we double this one, we're not changing that one, so therefore they're both going to stay the same. The only thing that happens is when we flip, we change the sign. But we never double, triple, half, anything like that to the cell potentials. So then finally, we just add all those together. So it's going to be 0.80 plus 0.25, which means that the E of the cell, in this case, is going to be equal to a positive 1.05 volts.